Okay, welcome to another operations research video. This one is a simulation example, simulating an inventory management problem. And so Randa is responsible for how many ladders should be stocked at the local hardware store. And she wants to analyze the ordering policy for those ladders. And ladders are pretty large, and so she doesn't want to keep too many on hand. But she does have some historical data. So she got last summer's data, and so she knows how many ladders were sold, or um, on how many days 0 ladders were sold, 1 ladder was sold, 2, 3, 4, 5 ladders was the most sold in a single day. And she's got it for 100 days worth of data. And so we can essentially say that there's a 15% chance that they'll sell 0 ladders, 18% chance that they'll sell 1 ladder, at least based off of historical data. Okay. For every ladder over 3 that fit in the display, so she sort of has a front of house display where there's going to be 3 ladders. Any extras are probably taking up space in the back room, and she's decided to put a carrying cost of $2 per day. So essentially, what's the value to her of that space that could be used by other inventory, and sort of kind of what's the warehouse space worth. She estimates that the value of what it's taking up is $2 per day. And then if she doesn't have any ladders, if she gets to a stock out and a customer comes and wants to buy a ladder but can't, essentially the store loses $100, both in the missed sale, so the missed revenue from selling that ladder, but also potential future business. And so usually you'd kind of assess a stock out with a penalty that's more than just the profit that you'd get from that one sale. And that it might affect future sales. If you get a reputation of not having things on hand, then people aren't going to come to your store. When she reorders ladders, there's a $20 per delivery charge, and so ideally she doesn't want to be ordering too many times. Otherwise, she's going to incur a lot of these delivery charges. So let's help Randa out and help her develop her optimal inventory model. She wants to know at what point to reorder. So if the stock drops below this level, she's going to reorder. And then when she reorders, what should her target be that she's reordering up to? Okay. Keep in mind there's a 3-day wait for ladders to come from the wholesaler. So she places her order, they only arrive 3 days later. Okay. And to begin time, she's got a current stock of 12 ladders, and we'll simulate another summer's worth of sales of 100 days. So let's start off by thinking about what's the state of the system and what are the possible states. Well, our state of our system should include her current inventory, right? It should also include any outstanding orders that she's placed that are sort of in transit. We might think of them as being maybe she ordered them 1 day ago, so they're 2 days out. Maybe she ordered 2 days ago, they're 1 day out, and so forth. And then what events can change the state of the system? Well, each day's ladders sold, kind of demand, reduces her inventory. So that event changes the state of the system. Also, if she places orders, that kind of changes her outstanding orders. And then also whenever orders are delivered, that changes her inventory. Okay, so those are the main events that change the state of the system, where the state is how much inventory she has, as well as how many ladders does she have on order, and essentially when are they expected to arrive. So thinking mostly about the ladders sold demand, how can we generate those random events? So looking back at her historical data, we've kind of got this record. There's a couple ways that we could simulate this historical data sort of happening into the future. The first is we could generate a random uniform number between 0 and 1. And so this 1 here just says we're generating just a single number. And then we can use a case when. And so this is a powerful way of kind of making custom variables. And if x is less than 0.15, so because x is between 0 and 1, if it's less than 0.15, that's a 15% chance. Then after the tilde is the value that we'll get out. Okay. And so there's a 15% chance that the result of this case when statement will be 0. And then I use 33 next because 0.15 plus 0.18 is 33. And so there's an 18% chance that she'll sell 1. And so we want to kind of add that percentage to the previous percentage, which was 0.15. Okay, and so the chance that it's bigger than 0.15 and less than 0.33 is 18% chance. And so there's going to be an 18% chance of selling 1 ladder. There's going to be a 28% chance of selling 2 ladders, and so forth. And so the way that the case when does is it looks at the first line. If the first condition is true, it outputs that. If the and is done. If it's not true, then it looks at the next one and checks if that's true. If it is, then it outputs that. Otherwise, it checks the next one. So it only checks each successive condition if the previous conditions are not true. And so the last one, I usually put a last condition that is just true, that guarantees that if none of these happen, then it's going to output the last one. And so if x is not less than 0.95, that means it's bigger than 0.95, but because of how it's generated, it's less than 1. So there's going to be a 5% chance that we'll sell 5 ladders. Okay, so here I'll kind of run that code and run that, and we can see, okay, this time we got 0 ladders, but if we generate another random x value and run the case when statement again, now we'll sell 1 ladder. Now we sold 2 ladders, just happened to be increasing, but that now we're back to selling 0 ladders and 0 ladders again. Okay, and so these 2 lines of code can kind of generate the demand on a given day. Another strategy that is essentially the same as this one is to sample from past events. So kind of here's our past events. We sold 0 to 5 ladders, and we sold them. This is how many times we sold each of that many ladders. And so if we run this, we'll get a vector of past events that if we were to look at that, let's maybe look at what that past events looks like. It's going to have 15 zeros followed by 18 ones, followed by 28 twos, etc. Okay, and so rep allows us to repeat the things in a list, and we can tell it how many times to repeat each things. So once we've got our list of past events, the sample function essentially draws from that. And so if we sample past events and draw just one value from that, that will give us one value from that list of the 100 outcomes that we had from the last summer. So there we got lucky. We sold 4 ladders, sold 3 ladders, sold 4 ladders, sold 2 ladders, sold 0 ladders. Okay, so we could generate ladders sold that way. If we had a historical data, we could sample from that historical data. So that's a pretty cool trick. The last way is we can think about, okay, I'm selling ladders, which is a countable number of events happening in a fixed period of time, so in a day. And as long as we treat and think that each day is about equivalent to any other day, that feels like it would be well modeled by a Poisson distribution. Okay, and so what we need for a Poisson distribution is the mean value. That's the lambda parameter. And so if we look at, here's that Poisson mean, it turns out to be 2.1. And then we can generate values from a Poisson distribution with mean 2.1. And then here we're going to get 2, 5, 4, 2, 2, 2, 1. Now, one thing about the Poisson distribution is that it doesn't have an upper bound. And so although in the 100 days that we looked, we didn't ever sell more than 5 ladders, if we generate Poisson, there is a chance, albeit a small chance, that we sell 6 or 7 or 8 ladders. It just gets very small the farther we get away from that mean value of 2.1 ladders per day. Okay. And so, yeah, we can use a Poisson distribution. And so if you think your situation matches up well with a known distribution, use that distribution. That's a good strategy to use. Okay. Now let's talk about the overall kind of pseudocode for simulating a single summer, right? So we'll say a summer is one simulation. For that summer, we're going to loop through 100 days of that summer. For each of those 100 days, we're going to generate the demand. We're going to resolve inventory. We're going to calculate any costs incurred. And then if necessary, we're going to order more ladders and move up any orders that are currently inbound. Okay, so it's a good idea to kind of, whenever you're planning out a simulation, sort of sketch it out on paper, make a flow diagram maybe of kind of what are the steps in the process that is one run of a loop. And then especially if you're simulating multiple days for one simulation, then think about how that repeats. Okay. So this is our strategy: generate demand, resolve inventory, calculate costs, order more if necessary. So I like to build up from small to large. Actually, I've maybe skipped one step here in how I would build this simulation, is I would just simulate one day, just see if I can get the code to run for a single day first. Okay. Once I got it running for a single day, then I'd worry about a whole summer. We're going to jump straight to a whole summer, and I'll kind of talk through kind of what's going on here. So first off, we've got our policy parameters. To begin with, I'm going to say she's going to reorder whenever the stock drops below 6. And if it drops below 6, she's going to order to the point where she would have 16. So if she ends up with 3 ladders, she'd order 13 more ladders so that her target inventory is 16. Now, because it's going to be a couple days until those ladders come, by the time they come, she'll have sold more ladders, and so she won't actually have 16 ladders really ever, unless she has a couple unlucky days where she sells no ladders in a row. But that's sort of our target. We're going to use a Poisson mean of 2.2 ladders per day as sort of the average number of ladders that she sells in a day. To be honest, that's the number that I use to actually generate this data. Okay, so this data I kind of randomly generated using a Poisson distribution to begin with. The average of those 100 days ended up being 2.1, but I think I left my code at 2.2 because that's actually the number that I used to generate them. So always a little margin for error there. And then I'm going to tell it that I want 100 days in the summer, but obviously I could change any of these to kind of change up the situation to reflect a different reality. So these are sort of our policy things that we can change if we want to look at different policies. We usually need to initialize the things that are going to change during the simulation. And so my current stock, I said she's got 12 ladders on hand right now. So that's what I'm going to use as my current stock. This vector is going to kind of keep track of the stock over time just for interest. Okay, I'm curious on kind of what does the stock look like over time. And so I created a vector that's number of days long, but is filled with all negative ones. And this is maybe a habit that I have, is that when I want to initialize something and I'm going to fill it in as I run the simulation, I like to initialize it with impossible values. So I know the stock's never going to be -1, but if I fill it in with -1s, then if the simulation isn't actually properly updating that stock vector, then I can see that it's still got a bunch of -1s in it. Okay, and so it doesn't really matter what number I put here, but I like to put something that's impossible just so I know whether things have been touched or not by the code. Okay, initially we're going to say the current storage cost is 0, stock out costs and delivery costs are all 0, and we have no outstanding orders. Okay, so this is sort of current costs and current outstanding deliveries are 0. So our state is really this current stock as well as these delivery amounts. Okay, I made separate variables for what's the deliveries that we expect in 1 day, in 2 days, and in 3 days. Okay, there's maybe a alternate way of having a variable for how much the delivery is and how many days till that delivery. That'd work as well. I just chose to do it this way. Okay. So for loops. I added a video specifically on for loops, but in general, they allow us to run code many times. And so I'm going to repeat this code for each day from 1 to number of days. Okay, and so I said num days is 100 days. And so this loop is going to go through 100 times. The first time day is going to be equal to 1. The next time day is going to be equal to 2, etc. Okay, so for loops, really powerful for simulation. So kind of thinking back to my pseudocode, the first thing I do on a day is generate the demand for that day. And so I'm going to generate it using a Poisson distribution. It'd be just fine if you generated it using one of those 2 other methods that we said we could use for generating demand. Okay, so once I've generated demand, then I'm going to update the amount of stock that I have on hand. So my current stock will be the previous current stock plus any deliveries that were 1 day out, because those arrived today, minus the demand for today. Okay, so anything that came in on today minus what went out is the change from the previous day. So that was the previous day's current stock, and now it's being updated with deliveries as well as demand. Okay, so once I've updated the stock, then I need to check whether it's negative. Okay, realistically, we can't have anti-ladders or negative ladders. And so if it's less than 0, it means that more people came in asking for ladders than we had ladders on hand. Okay, which means we should incur some stock out costs. And we said $100 per ladder. Note that current stock is negative. So if it's -2, that means we missed selling 2 ladders. And so we take -2 times -100 to get +200. Which should be the penalty, and we'll add that to our kind of running total of stock out costs. Okay, and we started that running total at 0, and so this kind of grows as we run into stock outs. And then since we can't have a waiting list of ladders, we don't have a waiting list of ladders, we set the current stock to 0, so we don't have negative ladders, but we just have 0. We incurred the stock out penalty. But those kind of customers that came in, we don't put them on a wait list. We just turn them away. Okay. We assume they went to the competitor's hardware store and bought their ladder instead of our ladder. Then we want to update our delivery orders. So everything that was deliver in 2 day is the new deliver in 1 day. Everything that was deliver in 3 day is now going to be 2 days away. And then we need to decide whether we're going to order. And the first time I wrote this code, I ignored the fact that if we place an order, we don't want to place another order the next day when our stock is still below our order level. Okay, so first thing we're going to need is we're going to need this order in, kind of a variable that is true or false and checks whether there's any orders in the pipeline. Okay, so it checks whether deliver in 1 day is greater than 0 or deliver in 2 days is greater than 0. If any or either is another way to think of those. If any of those 2 things are true, then order in is going to be true, and it's going to tell us, yes, there are outstanding orders. Okay. Now we decide do we make an order? And so what we want to check is we want to check if the current stock is less than or equal to our order when, kind of the level that we said. If we go below this, or the way I coded it up, if we go equal to this or below this, we'll reorder. But we'll only reorder if we don't have outstanding orders. And so this exclamation point is a logical operator that flips trues to falses and falses to trues. And so if order in the pipeline is true, if I put an exclamation in front of it, then it'll flip it to false. Okay, so we'll order again if we don't have orders in the pipeline. Okay, and our stock is less than or equal to the order when point. So the and is accomplished by those double ampersands. So both of these conditions have to be true in order for me to place an order. Okay, if I place an order, then I set the deliver in 3-day value to be whatever I want to order to. So the kind of the order target level minus whatever my current stock is. So if my current stock is 3 and my order to is 16, I'll order 13 ladders and those will go in order in 3 days. Okay. I said that each delivery incurs a delivery cost of 20. And I've decided to kind of implement those delivery costs when we order the ladders. Makes sense, rather than having to bookkeep and look at when they're going to arrive. And then if we don't place an order, then our deliver in 3 days is going to be 0. And so kind of we need to clear that variable if there's not any, if we don't place an order. Okay, then we're ready to update our storage costs. Our storage cost looks at how much stock we have on hand beyond the 3 that are in the display case. And so we're going to update our previous storage costs with a $2 per ladder that's beyond the 3 in the storage case. So if I take my current stock minus 3 and it's bigger than 3, that will tell me how many extra ladders I have in the back room. If it's less than 3, then this is going to give us a negative number, and the max of that negative number in 0 is just going to give us 0. So if we have less than 3 ladders or 3 or less ladders, we don't have any storage costs because they're all in the front of house ready to be sold. But if we have more than 3 ladders, there's some in the back of the house, and those are the ones that we're incurring a storage cost on. And then last thing, bookkeeping, I'm going to record the amount of stock on that day. Okay, so, and then here's the closing curly brace that goes with this for loop. Okay, so I encourage you to keep your kind of curly braces aligned. You'll notice if you click next to one, it'll highlight the other one. I'll show you later down. I often use a practice where I'll sort of annotate the closing curly brace with what it's actually closing, and I'll show you that further down in the code, which is especially important when you have a lot of curly braces because you have multiple for loops. So let's go ahead and run this chunk of code. After we run it, I'm going to plot the amount of stock on each day. And so here's the amount of stock on each of the 100 days of the summer. And so we said we started at 12, but I guess on the first day we had 4 orders already. And so we're down to 8. And then you'll see that it goes below 6 here probably by just the second day. And so we reorder ladders. The number of ladders keeps going down until 3 days later when it pops back up again because the order arrived. Notice that it only pops back up to 8 because on the day that it arrived, we also sold some ladders, and I think if we reordered at 6 ladders, then we probably ordered 10 ladders, and so on the day that they arrived, we got 10 ladders sold to, and so we got back down to 8. And so you kind of see this zigzag cycle going up and down of when we're placing orders and when they're arriving. You'll notice that a decent number of times we're hitting 0, where we're selling out of ladders and we've got no ladders in stock. And so we maybe want to choose a higher order when point than just ordering when we hit 6 ladders, because it looks like in the 3 days that it takes those ladders to come, we often sell more than 6 ladders. And then here I've gone ahead and printed out storage, delivery, and stock out costs, as well as the sum of those 3 costs. And so it looks like for this run of the summer, their storage costs were $614. The delivery costs were $400. And if there were 20 per, then it looks like we received 20 orders, which matches up with our picture here. It looks like there's about 20 times that our inventory went up. But our stock out costs, which is the third number here, was $2,400, and so much larger than the other 2 numbers. we missed out on the sale of 24 ladders over the 100 days. And so, yeah, that's not good for long-term business if we're not able to provide our customer with what they're looking for. And so then the sum of these three, kind of our overall cost of our inventory model, is 3,414. Okay, now if we run this again, and I'll use Control-Shift-Enter to run the whole thing again, I'll get a different inventory cost. So 3,214 was one possibility. 1960 is another possibility. It looks like this simulation got lucky, only had $900 in missed sales. And so you'll see it didn't quite bottom out nearly as many times in this run of the simulation, right? I'll hit Control-Shift-Enter again, run this again. And now it's 2,182. And so, and you can kind of see our inventory over time. And so each run of the simulation is going to give you a different realization of what's possible. And that's kind of the idea of simulations is you run it once, and that sort of shows you what's possible. And that's when you want to kind of debug and make sure the simulation is working. But then the next step is run it many times, okay? And so usually I'll say for the homework, run it 1,000 repetitions, and that will give you a good idea of the characteristics of what is the typical total cost, okay? And so that's what we're gonna do next. So scroll down. Now let's try it for 1,000 simulations. For each of those simulations, I'm gonna record the storage costs, the delivery costs, the stock out costs, as well as I'm curious about what the average stock is over time. You notice the stock goes up and down, but kind of what's the typical or average number of ladders that I have on hand? So not really necessary, but I was curious, and so I added it in there. Usually I'll make a data frame with all the things that are interesting to me about a single simulation that I want to record for all the simulations. And so in this case, I set num sims to be 1,000. And I've sort of pre-set up each of these as being a vector of length 1,000, and I pre-filled them with -1s, just because that's sort of my default value that I put in there, just to kind of double check the code, make sure that I'm actually putting a value in for each of those. Same policy parameters as before. Now we've got an extra for loop here that loops through sim in 1 through number of simulations. And so this loop is going to go 1,000 times. Now, inside this loop, we need to make sure that we always are refreshing the starting point so that each simulation starts from a fresh start with a current stock of 12 and 0 for the all 3 costs and empty orders incoming. And so that's kind of gets it set up. And then everything from here down this for loop is the same for loop we had before. It's looping through our number of days, the 100 days of our summer. Okay, so I'll kind of skip past that. Here's what I was mentioning about. I like to annotate the end of my curly braces. So this is the end curly brace for my day in num days for loop. Okay. So this is the end of one simulation. Then at the end of that one simulation, I want to store the results. So I'm going to, in my sim results, store the storage costs in storage costs square brackets with the sim number there, store my delivery costs, store my stock out costs, and take the average of the stock and store that in average stock. Okay. And I'm going to do that and then this curly brace is the end of the 1,000 simulations loop. Okay. So let's look at that. And then I've got some histograms of each of those quantities. So I've got histograms for the storage cost across the 1,000 simulations, delivery, stock out, and average stock. And so let's look at those. And so here's a histogram of the storage costs. So typical is about 800 to 900. And we see it's fairly normally distributed, kind of nice bell-shaped curve here. For delivery costs, tends to be about 300 to 340, which would be 15 to 17 deliveries. Okay. I guess I could have tracked number of deliveries just as well. For the stock out cost, we'll notice that's sort of right skewed in that when things go bad, they can kind of snowball into being really bad. And that's where we can get these really high stock out costs of, yeah, missing over 4,000 in stock out costs would mean we missed out on almost 200 sales over the summer. That's really, really bad. But maybe typical stock out costs is about 1,000, which would be missing. Oh no, we said $100 per. So this would be 1,000 would be missing 10. 10, 2,000 would be missing 20, and so forth. Okay. Average stock, typical average stock is having between between about 6 and 7.5 ladders on stock at any point in time. But note that, like, remember, some of that time I've got 0, some of the time I have a lot higher end. So really it's kind of doing the zigzag shape over time. And then what's interesting to me really is the total costs, where I added the other 3 costs together. And so this is a typical cost under this policy, and that kind of worst case scenario is about 4,000 in cost. But typical is about 2,000 to 2,500 in total cost for that policy. Okay. And then here I've kind of created a list with the mean total cost as well as plus or minus 2 standard deviations. And so the typical total cost is about 2,300 over the 1,000 simulations. And then if we kind of look at the middle 95% of simulations run between about 1,200 and about 3,400 in costs. And so 95% of simulations were between these 2 numbers. Actually, not exactly, because I kind of use plus or minus 2 standard deviations. You could actually count the number of simulations between 2 numbers, or kind of compute the percentiles would be maybe even a better way to do this. But this works. Not too much skew in this distribution. So adding and subtracting 2 standard deviations, not the worst thing. Okay. And so depending on your strategy, usually we're trying to optimize the expected or the average value. And so in this case, we'd probably want to minimize that average value. But there's other cases where you might want to minimize the worst case scenario. So maybe there's some you want to kind of minimize your kind of, the worst case. So you might want to try to minimize this number. Okay. So that was a simulation of one policy, but we've got some decisions on what we could do for that policy. And so let's sort of set up another set of loops that will loop through our policy decisions, namely that order when and order to variables. Okay, so setting up my sim results here, it's going to be an empty matrix, or that data frame for one policy set. But what I'm going to do here really is I'm going to look at an order when, looking at 4 through 10 as my possible points where I'll reorder. And I'll look at 15 to 25 as possible targets of what I'll order up to. I'll leave the mean for the Poisson distribution and the number of days at 100. And then I'm going to store the results, which are the total costs for each policy, in a matrix. And that matrix is going to have, let's see, what did I put? Rows is from the order when list and columns from the order to list. Okay. It may be clearest when I run this, and I'll show you the results. And I would say when it comes around to it, poke around a little bit in this code to kind of see what I'm doing at each step here and see what the variables create in the environment over here. Okay. So I've now added essentially 2 more for loops around it, looping through my order when and order to list. And so those will change each time. So let's go ahead and run this. Here, I'll run it and then I'll point out one more thing. So then the thing is that once I get done with 1,000 simulations at the current policy, then I record the policy results. And I essentially put it in the right place in the policy results matrix. There's maybe other ways to do this, but what I'm recording is the total cost for that simulation. Okay. So here's the policy results here, but it'll be a little bit easier if I just go into here and click on policy results and open them up here. And so this is, each of these entries is the average total cost for that policy over 1,000 simulations. So sort of each of these represents 1,000 simulations that was done. And so you can tell quite a lot of simulations were done. Thankfully, each one didn't cost much in time. And so it ran relatively quickly. But you can kind of see that if you have a decent range of policies that you want to test out and you want to do it for a decent number of simulations, it adds up fast in the kind of computational time that it takes to run these simulations. So let's maybe kind of look kind of visually through this to kind of try to find the minimum total cost. And so what I'll notice is that if I set my order to, let's do the order to at 16, because that's what we had it set to begin to initially. And then if I look at it, if I have the order when really low, it will stock out a lot and I'll have a really high cost. And so it goes down, down, down as I'm going down here. But it looks like in this column, the minimum is when order when is 9. And actually, if I look across columns, order when equals 9 is usually the lowest in that column. Okay. And now as I start moving across columns, I think my best results happen right here when order when is 9 and order to is 18. And so kind of looking at it, all the ones nearby are worse than it. If I set my order to really high, I'll have a lot of stock on hand. And so I'll be incurring a lot of carrying costs. If I set my order to low, then I'm going to have to be placing a lot of orders. And so I'm going to incur more order costs. And so it looks like the happy medium is to order whenever the inventory drops below 9 and order towards a target of 18 ladders. Of course, now some of those ladders will sell before the order arrives. But yeah, it looks like the average cost under that policy is just under 17,000. Now, the kind of margin of error from these simulations, because there's randomness, if you rerun these simulations, you'll get slightly different numbers. You can mitigate that by having more simulations, but that costs more. And so some of these might be essentially equivalent solutions where having an order to target of 17 might be just as good as having an order to target of 18. And so you can use kind of other judgment criteria to help break the ties in that case. Okay. So this was a pretty full example of a simulation study for an inventory model, kind of walking you through kind of running one simulation, running a bunch of simulations, and then potentially looping through policy choices. Okay, that's it for this video. I'll see you in the next one.